Imagine for a moment standing beneath a vast, inky sky studded with countless points of light, each one a distant sun, a galaxy, a universe unto itself. For centuries, humanity has gazed upwards, seeking to understand our place in this grand cosmic tapestry. We've learned so much that these galaxies are not static, but are in constant motion, drifting away from us and from each other. The universe, we know with certainty, is expanding, growing larger by the second. But this fundamental truth, as profound as it is, hides an equally profound mystery, precisely measuring the speed at which this colossal expansion is occurring. This expansion rate is quantified by a value known as the Hubble constant, named, of course, after the pioneering US astronomer Edwin Hubble. He was the one who first provided observational evidence that the universe is indeed expanding. But here's where our cosmic dilemma truly begins. Scientists have developed two primary methods to calculate this crucial constant, and, troublingly, they don't agree. One method relies on observations of the nearby universe, measuring the distances to supernovae and the recession velocities of galaxies relatively close to us. The other method delves into the very early universe, analyzing the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself. When we use these two different lenses to peer at the universe, they yield significantly different results for the Hubble constant. It's as if two perfectly calibrated stopwatches timing the same race consistently show different finish times. This discrepancy, while seemingly a technical detail, hints at a potential flaw in our understanding of the universe, or perhaps an entirely new physical phenomenon yet to be discovered. This Hubble tension, as it's known, is a whisper of the unknown at the very foundations of our cosmic model. For years, cosmologists have wrestled with this tension, exploring countless theories and hypotheses. But now, a fascinating new possibility has emerged from the depths of space and time itself, one that offers a fresh perspective, a potential cosmic Rosetta Stone to unlock this riddle: Dark Sirens. The name itself evokes a certain mystery, doesn't it? And fittingly so, for Dark Sirens are born from some of the most dramatic and cataclysmic events in the universe. Imagine two colossal stellar objects, perhaps two black holes, with gravitational pulls so immense not even light can escape. Or two incredibly dense neutron stars, the collapsed cores of once massive suns. Spiraling inward, locked in a death dance. They collide with a force so unimaginable, so utterly overwhelming, that it doesn't just produce light or sound, it literally warps the very fabric of space-time around them. These astronomical distortions, these ripples in the universe's tapestry, are known as gravitational waves. They were first theorized by Albert Einstein over a century ago, but remained elusive, a beautiful prediction without direct proof, until relatively recently. Then, in 2015, a groundbreaking moment in scientific history occurred. The LIGO detector, a colossal experiment designed to pick up these faint cosmic tremors, finally registered the distinct signal of two black holes merging billions of light years away. It was a triumph, opening an entirely new window onto the universe. The era of gravitational wave astronomy had begun. Now, this is where Dark Sirens truly become relevant to our Hubble constant problem. When these immense collisions happen, especially those involving neutron stars, they don't just send out gravitational waves. Sometimes they also produce brilliant flashes of light, powerful bursts of electromagnetic radiation that can be picked up by our traditional telescopes here on Earth. This is the crucial synergy. Think of it like this. The gravitational wave signal acts as a precise cosmic ruler. From the characteristics of the wave itself, scientists can calculate with remarkable accuracy how far away the event occurred. At the same time, if that event also produced a flash of light, our telescopes can measure how quickly that light is moving away from us, a phenomenon known as redshift, which tells us the expansion velocity. By combining the precise distance measurement from the gravitational wave with the precise speed measurement from the light, scientists can directly calculate the Hubble constant for that specific patch of the universe. It's a truly independent method, free from the assumptions and systematic errors that plague the other two. However, the current limitation is that not all gravitational wave events produce an observable burst of light, and pinpointing the exact origin of a light flash can still be challenging. But this is where the future of Dark Sirens becomes incredibly exciting, holding the promise of a complete breakthrough. Researchers are filled with hope that as gravitational wave detectors become more sensitive, more numerous, and more sophisticated, our ability to pinpoint dark sirens will dramatically improve. The ultimate goal, the true game changer, is this. In the ever-evolving field of gravitational wave astronomy, scientists envision a future where we won't even need that burst of light. We will be able to detect the gravitational wave signal from these merging black holes or neutron stars, understand its properties with such clarity that we can calculate both the distance to the event and its recession velocity solely from the gravitational waves themselves. Imagine a universe with its own built-in gravitational speedometer. This would provide an entirely new, pristine method for calculating the Hubble constant, independent of all previous techniques. If this new approach aligns with one of the existing measurements, or even if it presents a third distinct value, it would offer invaluable insights into the fundamental nature of our expanding cosmos, perhaps revealing entirely new physics. So, the next time you gaze up at that boundless night sky, consider the incredible forces at play, the immense mysteries yet to be unraveled. From the violent, beautiful dance of colliding black holes and neutron stars emitting these dark sirens of spacetime, we may just find the key to one of the universe's most enduring puzzles, the true speed of its expansion. It's a testament to human curiosity, to our relentless pursuit of knowledge, that such cosmic cataclysms could hold the answer to understanding our place in the universe. What are your thoughts on this fascinating possibility? Do you think dark sirens will truly solve the Hubble tension, or do you believe other answers lie hidden in the cosmos? Share your ideas in the comments below. If you're as captivated by the universe's secrets as we are, please consider subscribing for more cosmic journeys. Until next time, keep looking up.